What is the difference between thixotropy and pseudoplasticity? Imagine a fluid that changes its thickness depending on how you handle it. Some fluids become runnier the more you stir or squeeze them, but they do it in different ways. That's where understanding the difference between thixotropy and pseudoplasticity comes in. Both are behaviors seen in non-Newtonian fluids, which don't follow the usual rules of liquids like water. Instead, their viscosity or thickness depends on stress or time. Thixotropy is a time-dependent change. When you apply a steady force to a thixotropic fluid, its viscosity slowly decreases. Think of it like stirring honey that's thick at first but gets easier to pour after a few minutes of stirring. Once you stop stirring, the fluid doesn't instantly return to its original thickness. Instead, it gradually rebuilds its structure and thickens again over time. An everyday example is ketchup. When you shake or squeeze the bottle, it flows more easily. But if you leave it sitting, it thickens back up, making it harder to pour. This behavior happens because the internal structure of the fluid breaks down under stress and then slowly rebuilds when the stress stops. Pseudoplasticity, on the other hand, is all about how fast you apply force. It's a shear rate-dependent change. When you increase the shear rate, meaning how quickly you deform the fluid, the viscosity drops immediately. This is called shear thinning. For example, many gels and creams flow easily when you spread them on your skin. But once you stop spreading, they instantly regain their original thickness. This quick response makes pseudoplastic fluids very handy in products like lotions and paints, which need to spread smoothly but stay in place afterward. To sum it up, thixotropic fluids become less viscous over time when stressed, then slowly recover their thickness. Pseudoplastic fluids become less viscous instantly when you increase the shear rate and quickly regain their original state when the force lessens. Some substances even show both behaviors at once, making their flow properties quite complex. This is part of what makes non-Newtonian fluids so fascinating in fields like cosmetics, food science, and materials engineering. Their ability to change viscosity based on time and force helps explain many everyday experiences, from how paint spreads to how certain foods behave.